please welcome János Selmeczi here on the stage. Give him a warm applause. János is a long-time contributor to the SDRA, and I'm very happy that he's here with us this year again, and live here in Friedrichshafen. And János is going, well, he's been working on frameworks, on streaming frameworks, which was a fantastic work. I was very happy to have that here. And János was now working on PLLs in SDR, and I give you the word.
Yeah, good afternoon. In this presentation, I will talk to you about PLLs in SDR programs and a Python software package, PLL-Pi. Now, what is this PLL-Pi? It's a software package written in Python, and it will help you to make experiments and learn how software PLLs are working. It contains a lot of algorithms what you need to implement PLLs. It contains 3 different PLL loops and all the testing environment to test those loops. It's an open source, and you could download it, clone it from GitHub. In the first part of this presentation, I will talk to you about the behaviors and the features of software PLL. In this slide, you see the block diagram. The PLLs essentially control loops which tracks the phase embedded in a complex exponential function. This why the PLLs are nonlinear devices. And if you like to analyze the PLLs, you have to have linear models. You linearize this nonlinear model. How to do it? Essentially, you pull out the phase from the complex exponential and replaces the mixer, the low-pass filter, and the phase detector with other substructor. And finally, you have to replace the numeric control oscillator. What is this oscillator essentially do? It's integrate its frequency control to have the output phase. So you replace the NCO with an integrator. You could have linear models for various domains. These domains could be the discrete time domains, the Laplace domains, and the Z transformation domains. And actually, you could do the analysis in each domains. You choose that domains in which the particular problem is most easier to analyze. Okay, the PLLs are control loops. That means that you have the same transfer functions, what the control loops are. Okay, the first is the open loop transfer functions, which relate the output phase to the error. The system or closed loop transfer functions, which relates the output phase to the input phase. And finally, you have the error transfer functions, which relates the phase error to the input phase. The dynamic behaviors of the PLL is determined by its loop filter. We could have three type of PLLs, type 1, type 2, and type 3. The number designates how many integrators you have in the open loop transfer functions. And because the open loop transfer function contains the integrators in the NCO, that's why in the loop filter you have one less integrator. That's why in the type 1 PLLs, you have no integrators. In the type 2, it's one integrators, and the type 3, it's two integrators. It's very important that in software PLLs, we use ideal integrators. This is very different from the analog PLLs, because in the ideal integrators, you have a zero, you have a pole at 0 on the Laplace transformation plane, and in analog PLL, you cannot have such an integrator. You have to approximate it. Here you could see the open loop transfer functions. On the left side, the type 2 PLL, right side, type 3 PLL. Because it has two integrators, the curve starts with a 40 dB per decade descent. At omega 0, you have a 0, so the curve changes to a 20 dB descent. And if the PLL is correctly designed and it's stable, this 22 dB descent should cross the unity gain line. The bottom part, you could see the phase transfer function. It started at minus 180 degrees and end up at minus 90 degrees. And you could see at the unity gain how we define the phase margin. On the right side is the same thing for the type 3 PLL. There is a very important parameter of the PLL. It's a noise bandwidth. It's a single-sided bandwidth. You could imagine it that way that you have a filter which has the transfer characteristic of the open loop transfer function, or no, closed loop transfer function. And you connect a noise generator at the input. This generator gives out white noise, and you measure the noise power at the output. Now you make a brick wall type low-pass filter with a variable cutoff frequency, put the same noise source into the input, and you measure the output noise power, and you change the cutoff frequency until the output noise power will match the previously measured noise power with the closed loop transfer function. And in that case, this cutoff frequency will be the PLL noise bandwidth. It's a very important parameter because the phase noise on the NCO output will depend on this bandwidth. And the higher this bandwidth, the higher the phase noise will be. There are other features of the PLL which depend on this noise bandwidth. Here you see the locking process for a PLL. On the left side with a 4 Hertz noise bandwidth. On the right side, it's an 8 Hertz noise bandwidth. You see, if you increase the bandwidth, the PLL will lock faster. That's one thing. And the other thing, if you see the maximum phase error, Okay? If you increase the bandwidth, okay, the maximum phase error will decrease. It's almost linearly. There is another important things which related to the noise bandwidth. It's the delay in the loop. In the analog PLL, you rarely have to deal with these delays. In software PLLs, you could have a lot of problems with that. The delays could come from two sources. One of the delay due to the software signal processing implementation, and the other source is due to the low-pass filter which follow the mixer. Okay? The low-pass filter could have group delays, and this group delays is actually a delay in the loop. In this experiment, I used a 4 Hertz bandwidth and increased the delay, actually increased the filter length. And you could see that if the delay start to increase, there start an oscillation and the settling curve, which will grow. And finally, the PLL will be completely unstable and won't lock. That's a very important thing, and there is only a few papers which dealing with this phenomenon on the internet. This is the other experiment. I fix the delay, and I start to increase the loop bandwidth. And you could see the same phenomena. As the loop bandwidth is increasing, an oscillation is starting in the error settlement curve, and finally the PLL will be completely unstable. The latest thing, the noise bandwidth will influence some of the internal signals in the PLL loop. Okay, here we use a very bad signal-to-noise ratio, a -27 dB and a 200 kilohertz bandwidth, which is a +10 dB at the input of the phase detector, because we have a low-pass filter with a cutoff frequency of 20 hertz. And you could see the PLL will lock, and at this point, okay, I reduce the noise bandwidth from 4 hertz to 0.125 hertz. It's a 32 times decrease. And you could see that the NCO control line, it's eliminated, the noise is decreased, almost eliminating the noise. But at the phase detector input and the phase detector output, the noise won't change. That's one other interesting thing. If your phase detector is sensitive, very sensitive to noise, in that case, the only thing what you could do to reduce the bandwidth before the phase detector. Okay, usually we use the noise bandwidth and the phase margin as the input parameters for the loop filter design. Here you could see the expression what you could use it. Actually, a summary, if you increase the noise bandwidth, the PLL will be locked faster, the phase noise will be larger, and the PLL will track in a better way the changing of the input phase. Okay, for the phase margin, if you increase the phase margin, the PLL will be more stable, more robust, the settling curve will be more flatter, but a little bit will increase the locking time. There is another major things with the PLLs, it's how it tracks the input phase changes. You could analyze it using the final value theorems of the Laplace transformation or the Z transformation, but it's a little bit complicated. So instead of this, I will show a table with the final summary results. For the type 1 PLL, it will track a phase step with a final 0 phase error, but won't step the other changes. For a type 2 PLL, it will track the phase step and the frequency step with a final 0 phase error, and the type 3 PLL will track the phase step, frequency step, and a linear frequency change with a 0 phase error. For frequency acceleration, which is actually important if you have some satellite-related application, okay? Because in most cases, the Doppler shift could be approximated a sine wave. In that case, you have frequency acceleration. Okay? For frequency acceleration, the type 3 PLL will have some phase error. This phase error will be proportional with the acceleration and will be inversely proportional with the third power of the noise bandwidth. That means that if you have a big Doppler shift and speedy change, in that case, you have to increase the noise bandwidth. Here is some experiment, okay, that's for type 2 PLLs. On the top row, it's the tracking of the phase step. That is when you have the phase step, there will be a transient in the phase error and the frequency control, and after it will be settled down. On the bottom row, you have the drawing for frequency steps. The same thing is true. When the frequency steps occur, you have a transient on the phase error line and on the transient on the NCO control line. After it, both will be settled to 0 error. That's for type 3 PLL. It's how it's tracked a ramp. This ramp is generated by a triangle wave. You could see when there is a slope changes, it will be phase transient, and it will be some small transient in the frequency tracking. That's for the sine wave shape frequency sweep. Once again, when the sweep starts and stops, you have a transient. But after the transient, the phase error, it's a sine wave shape. And on the top row, we have 4 Hertz loop bandwidth. On the bottom row, we 8 Hertz loop bandwidth. And the phase error, the maximum phase error, it's lowered 8 times between the two. Okay, here are some literature which you could use to study the PLLs. I highly recommended Mr. Gartner's book, The Phase Lock Techniques. It's a very important book because it's contained the materials about type 3 PLLs. Okay. Now I will talk a little bit about this PLL-Pi software package. It's written in Python, and its content, you could see a lot of algorithms, and the 3 types of PLL loops. It's important things that it has a common programming interface for all the algorithms and all the loops. The algorithm and the loops are working on sample-by-sample basis. Okay, there is no block processing. I choose this because we have to keep in a minimum the implementation-dependent delays in the loop. That's why there are some tricks for those algorithms which has different sample input and output samples, for example, a decimator. It's working in such a way that it's get all the samples, and there is an output flag which assigns that there is a new valid output samples. And between the 2 flags, it will output the last valid samples. Okay, some of the algorithm. It's very, very shortly. This is a moving average filter. It's a very tricky algorithm. It's called cascaded integrated and comb algorithm. It has actually the filter, what is do, it's for an output sample, averages the n previous input samples. But in this implementation, it don't have to do the whole averaging for every samples. It has a continuously running integrator, and it has a delay line on the input samples, which delay the input samples by n, and the output of the delay line is subtracted from the input of the integrator. So the integrator will contain always the sum of the n previous samples. That's a very tricky thing. Okay, here is the algorithm for a field decimator. Actually, here the important thing is that in the field filter, okay, if you decimate the output, you don't have to compute those samples which you throw away. Okay, if you your decimated factor is n, in that case, you have to compute only every nth sample. And this algorithm actually stores that. We have to use a vector which length is equal to the filter length, which is have to be higher or equal to the decimation length. And in that, I will store the necessary samples for the convolution. And do the convolution only if I have to output a valid output samples. I have a very special decimator which uses a moving average filter, but the averaging length, and that's why the decimation factor is not a fixed number, but it uses an external trigger signal. The trigger signal starts the averaging cycle, and the next trigger signal stops the averaging. The filter compute the output samples, reset it in several variables, and start the new averaging cycles. It should be used if you have to synchronize to a PAM encoded bit stream. I use a very special phase detector that's really different from the analog phase detector. First of all, it's compute the phase angle of a complex vector, but it compute the real phase angle. In the analog phase detector, usually output the sign of the phase angle. For a single sample, okay, it could only compute the principal value of this phase angle, which is in the range of -pi to +pi. But if it's get a series of input vectors, actually a rotating vector, in that case it could detect when there is a phase wrapping at pi or -pi, and use a phase accumulator, which at wrapping it's add 2pi or subtract 2pi from this accumulator, and that's why it could output the real phase. Okay, I have such an application when there was a transient phase error around 500 radian. And that means that it will track the input signal and won't sleep any input signal cycle. That's very important thing, especially if you had digital modulation. There is one important thing with this detector, that it could be used with BPSK or QPSK modulated carriers. For that, the trick is that in BPSK modulated carriers, I compute the square of the input vector. For QPSK carriers, I compute the force power of the input vector. And that means I multiply the phase angle by 2 or 4, and this multiplication will eliminate the phase changes due to the modulation. And at the output, I have to divide the phase angle by 2 or 4. And for QPSK, because the modulation mapping is for pi and not 0, that's why I have to subtract half pi from the output. That's a very, very, very tricky phase detector. Actually, what detect if you have a PAM, the pulse amplitude modulated signal, which has a +1 and -1 signal levels. Okay, it detects the level changes. That means the edge of the signal, and compare it compare it to a reference clock and compute the time differences of the edges. Actually, what I use it uses integrators and so on, but this method, it's will equivalent Mr. Gardner's method, which published in 1986. I will go through this algorithm very fast, but on the GitHub site, I have a very detailed description of this algorithm. You could go to the GitHub site and read the detailed description of the algorithm. Okay, this is the loop filter. That's the type 2 loop filter. Actually, it has an integrator and the error bypass, and the multiplication with the proportional gain is after the filter, and in the last stage there is a correction which you will need not to have a transient when you change the loop bandwidth. That's one and very tricky things, and really there is no published paper on this on the internet. The same thing is the type 3 loop filter. Actually, it have the same stages what in the type 2 cascaded, and once again at the end the multiplication with the proportional gain and the correction. Now why this correction you need? Okay, you could change the integration gain freely. It's no problem, okay? But if you consider only a block which only do multiplication, okay? There is an input signal, output signal, and there is a multiplication. And you change the multiplication factor. And if you keep the input signal constant, you change the multiplication factor. In that case, the output will change. There will be a step on the output, okay? And because this step will be on the NCO control line, this will be an equivalent to have a frequency step in the input. And if you reduce the bandwidth of the PLL, okay, at this step there will be a transient, but the bandwidth will be very small, and the settle time will be very large. And that's why you need a method to avoid this transient, and that means that you have to linearize, change the slope of the transfer curve in such a way that the transfer curve will go through the working point when you change the multiplication factor. And in that case, you won't have this step. Okay? And there is one more trick. If you have very large noise, in that case, you still could have some steps due to the noise spike. And that's why you, on the y-axis, on the working point, you have to use the previous n-sample average, not the actual value. Here is one of the implemented loop. Actually, it's a combined loop for unmodulated carriers, BPSK modulated carriers, and QPSK modulated carriers. The only modulation dependent thing is the PD type parameters of the phase detector. All the other thing is the same, okay? And that's why the loop topology it's very different to the usually used Costas loop topology. But actually the working principle, mathematically, the working of this loop is the same as the Costas loop. Okay, this is a very interesting thing. It's a frequency lock loop. Okay, it's the topology, it's very similar to a PLL loop. The only difference is that it has a frequency detector, not a phase detector. And after the loop filter, it has an integrator, an additional integrator. And that's why the dynamic of this loop, okay, will be the same as the PLL loop with the same loop filter. Okay? And this loop will track only the frequency of the input signal, not the phase. Okay? In a project, we used it for the initial locking of the PLL because we have to lock for a very wide range of input signals. And we cannot do that with a normal PLL because due to the very bad SNR, we have to use a very small bandwidth before the phase detector. And that's why we used this frequency lock loop for the initial lock. When the frequency was locked, okay, we switched off the frequency loop and hold the output control signals and switched on the phase lock loop. And after that, it will lock for the phase very fast. Okay, that's some results of the frequency lock loop. Okay, it is a locking for an initial frequency error. What could see the frequency error here is the NCO control. It's very similar to the drawings of the PLL. Okay. This is a bit recovery loop, which you could use for PAM, modulated bit stream. Actually, this version, this implementation, you could use with a rectangular pulse shape only. But you could change it to use it with other type of pulse shapes. It uses this edge phase detector. It's an important thing for this detector that if it won't detect an edge, in that case it will output a 0 phase error. Here you could see the test results. Okay, on the top row for a -1 +1 repeating bit sequence. That means that the phase detector always will detect an edge. It's once again very similar to the normal PLL. Here you could see here that for a random bit sequence, in average, for every other bit, there won't detect an edge. And that means you have it 0 levels. And that's why only the envelope of the curve we resembled for the curve at the top row. This is for phase error. And this one is for a frequency error. But actually, it's the same thing. And this loop is implemented in the NumPy package. You could experiment with it. Okay, the NumPy package was developed on Linux. I used Ubuntu 20.04. for the developing, but I tested on Ubuntu 22.04. You have to install some prerequisites, the Git, the Python 3, and 3 Python package, NumPy, CPy, and matplotlib. After that, you have to clone the GitHub repository. After you get the software, from the directory where you clone the software, you have to start a Python 3 console, and you have to follow these instructions, okay? That will run a PLL test for an unmodulated carriers and the initial frequency offset. And if you run this, you have to see these 3 drawings. Okay, the first one is the input signal of the phase detector. The second one is the frequency control signal of the NCO, and the third one is the phase error signal. And on the GitHub, there are test instructions for a lot of other scenarios. You could duplicate here this tracking scenarios, what I showed you. You have to duplicate these bit synchronization scenarios, the FLL scenarios, and everything is documented in details over there. So that's the...
Yeah. Thank you very much, János, for the nice talk. It was a basic talk, and I'm very proud that we have one of the basic talks about filters and some control units. It is very important for most of them. So we gave you 45 minutes to hold the talk. Maybe somebody gets nervous, says, well, he must finish. No, it is planned after the timetable. Thank you very much. So we are now starting for the questions. Are there any questions from the audience?
I have 2 questions. I was wondering, because your FLL uses an FFT, as I saw, doesn't that introduce a very long delay in this algorithm that just reduces the loop bandwidth a lot?
No, actually, there is no problem with that if you choose appropriately the sampling rates.
What do you recommend to use? What block lengths for the FFT? How many samples?
I used 4,000.
4,000?
4,096. That's the block length.
So if you have 200 kilo samples, this means, yeah, I'm not quite sure, but it will be...
Some hertz.
Yeah, it is some hertz.
Some hertz.
Yeah. And the delay of some hertz.
Actually, in the normal PLL, actually I have 40 hertz bandwidth before the loop detector, before the phase detector. The low-pass filter has a 20 hertz cutoff frequency. And actually in the normal PLL, I have around 1,250 decimation factor. So this FLL a little bit slower, but it's still work. And actually, the filter lengths in the normal PLL, it's 5,000.
Okay, thank you. This was the first question. Is the second question?
Yeah, the second question is if your library also provides some algorithm for the first, well, parameter values to begin with. Is it, I mean, there are some hints like Ziegler-Nichols or something like that for correct settings of PID parameters. Does your library also provide some functions to get the first set of parameters to get a better tuning or some auto-tune functions or something like that?
For the initial of the working process, there should be some estimated parameters inside it. It is any special initialization of your control algorithms?
No, actually, the everything what you need. Okay, I could parameterize the implemented loop. Okay, I have to give the sampling rates, the carrier frequency, the initial frequency offset, the initial phase offset. I could give as a parameter of the
This is initialization.
the decimation ratio, the length of the decimating filter, and so on. There are a lot of parameters. That's all, once again, is documented in the description on the GitHub. You have to read through this description, and that's why if you see when you create a loop, okay, an instance of a loop, okay, you have a very large command line for that, with a very lot of parameters. And of course, there are some parameters which you could change during a runtime. One second.
I think we should look on the time, and we are coming to the end. Are there any more questions? I hope. Yeah, there is one.
We are really late.
I think we should avoid that, and maybe you can discuss with him in private.
Actually, one more thing is that most of these algorithms have been implemented for FPGA in the last 1.5 years. We designed a transporter for a satellite, and for that we implemented lots of these algorithms for FPGA.
And in VHDL?
It's mostly VHDL.
Okay. So thank you very much, János. I want to say
Thank you very much.
warm applause. Thank you for the discussion. And we are now running out of time.